Hello and welcome. In this video, I will examine the 8051 stack in more detail and look at how it operates. I will, where possible, use programming examples to illustrate my explanation. So let's start off with a recap of the 8051 internal structure. And I would like to zoom in on the internal RAM, which is this part here. Now, the internal RAM is divided into two parts. The lower 128 bytes and the upper 128 bytes. And I would just like to concentrate on the lower 128 bytes. This is the lower 128 bytes. As you can see from this diagram, it's divided into different parts, and I would just like to focus on this area here, which is actually from 00 hexa all the way to 1F hexa. And this area of memory is divided into bank 0, bank 1, bank 2, and bank 3. And let's look at bank 1. Bank 1 is designated as the stack, and basically there are 8 locations, memory locations, stretching from 08 hexa all the way to 0F hexa, which is this area here. And 08 is register 0 or R0, and it goes all the way up to R7, which is actually the memory address 0F hexa. Now, how is this related to the ADSIM51? And here's the screen capture of the ADSIM51, and I just like to focus on this part here, the data memory part. All right, and I've repeated the stack area here, and I've extracted the data memory portion of the 8051 and displayed it here. So how does this thing related to this data memory? All right, so now this is from 08 all the way to 0F, which is basically the stack area. All right, so and for completeness, let's look at the other banks. So this is bank 0, this is bank 2, and this is bank 3. Okay, so let's look at the 8051 stack operation. I'll start off with this demonstration example or code. Like any of my programs in my previous video, I'm starting my program at 0000 hexa. Now, I just want to make a point here. When you first power on the 8051, the default start address is always 0000 hexa. And that's why you will see in some textbooks and code that you see for the 8051, they do not bother to put this in because the assembler will automatically place your code at this address, because that's where the 8051 expect to see your code starting point. Now, in this example, I've put at 0000 hexa this instruction ljump main, and basically when we execute the program, it will look at this instruction, and then it will jump to this part, the main, and I specify the main to start at 0115 hexa. All right, basically I'm just demonstrating that you can start your main program in any part of the internal ROM. So I've chosen to start in this particular demo at 0115 hexa. And basically the program here basically outputs a binary pattern to P1, which is the LEDs, and then jump to this part called test code, which is this part here, and this portion of the subroutine starts at 0205 hexa. And basically the subroutine output a binary 0 F hexa to the LEDs of P1 or port 1. And then once this is done, it will jump back to the main program, which is this part here, output another binary pattern to the LEDs, and then it stops. Okay, so we're back in the EDSIM 51, and I've uploaded the code here. I have not assembled it yet, so let me switch over to code memory. I'm now going to assemble the code, and we should see the hexa code appearing in the code memory. Just a quick reminder, when you power up, the 8051 will be pointing to 0000 hexa, which is the starting point here, and PC should reflect that. You should see 00000 hexa, which is already doing so. Power on. But the first instruction that I'm going to place here is the L jump to the main, which is 0115 hexa. So I need to adjust this to see the rest of the hexa code. So let me just assemble it first. Right, and you see the hex code for L jump main. So the opcode is 02, and you can see the address 0115, which is here. Right, so starting at 0000 hexa, these hex code which says L jump to main. Now I need to adjust this one here to see the rest of the code, because it's a little bit further down. So 0115, enter, and here we are. So the hex code for this portion of the code, of the source code, is here. So that takes care of the code memory. We got the code uploaded. Let's switch to data memory. Now, before I go any further, I need to point out a couple of things. So we need to focus on keeping watch on this part of the data memory. Why? Because that's the stack, which is bank 1, and it starts from 08 hexa all the way to 0F hexa. So we should be watching this part here. And also we should keep an eye on the program counter, which is this register here. All right, so it's already pointing to 0000 hexa, which I mentioned that earlier when we were looking at the code memory. So right, this now is assemble, and I'm going to use the step function here to step through the entire program. Now PC is already pointing at 0000 here. All right, so I'll execute this instruction. All right, now watch. Observe the contents of the PC. The program counter is now pointing at 0115, which is the start of our main program. And the first instruction basically is to load this binary pattern, or copy that into P1, which are the address of the port address of the LEDs here. So watch out for that when I execute this instruction, and watch for the PC. Watch out for the PC. The PC should be pointed to 0118. Why? Because that's where the next instruction is. Alright, so watch the PC and look out for the LEDs. Alright, so we've got the LEDs switched on, and the PC now is pointing at 0118 hexa, which is this location here where the next instruction is. The next instruction happens to be a call to a subroutine, TST code, which is this one here. So when I execute this instruction, it will jump down to here. Alright, and the PC should be pointing to 0205. So let's execute this instruction. Yep, PC is now pointing to 0205. Now, before I step down the code, watch out for the stack area. Notice at this stack area 08 and 09, we have these two values, 1A and 01. This is the actual return address to the main program after this subroutine has finished. Where is the return address? The return address is here, 011A, because when this is complete, the next instruction in the main memory, in the main program would be here. So this is known as the return address. But notice how the return address is stored. The low byte, which is 1A, the lower nibble, which is 1A, not nibble, byte, 1A is stored first, and then followed by 01. Alright, so this is how the return address is stored onto the stack. Right, now the program counter is pointing here. Now I will execute this instruction now, which basically load this binary pattern onto the LEDs. We should see a change in the LED patterns. Alright, so we've got it now. Now PC, now the program counter is pointing to this location here because that is where the next instruction is. However, the next instruction here is a return to the calling program, which is the main, so which is this one here. Now, how does it know where to go? It will have to refer to the stack for the return address. So watch out for the PC now when I execute the RET or return instruction. It should be pointing at 011A. This part here. Watch. Yep, it does. And notice the program execution has come back to the main program here. It will now copy this binary pattern onto P1. Watch out for the change in the binary pattern here. Yep, it's done it. And it stops here because this is a jump to this location forever. So it will stop here. So that's it for this demo. Okay, let's take a look at another example. And this is very similar to the previous example, except for some minor changes, minor addition here, and an additional subroutine. Now I'm starting this code again at 0, 000 hexa, and place this this instruction ljump main at that address. So once the CPU sees this instruction, execute this instruction. So the main now starts at 0115 hexa. Place this value onto P1, then call this subroutine TST code 1, which is this one, this subroutine here, and TST code 1 starts at 0205 hexa. Place this value onto P1, port 1, and then call this subroutine TST code 2, which is this one here, which is this subroutine here, and this subroutine starts at 0215 hexa. And in this subroutine, it places this this hex value onto P1, and then once that is complete, it then return back to this part of the TST code 1 and place this value onto P1, and then once that's done, it's get this return to the main and places this hex value onto P1, and then it stops here. Now, one thing to take note is that this subroutine here has to return back to this subroutine that calls this in the first place. It mustn't go back from this point here back to the main. So it has to go back to the calling subroutine, and then this subroutine will have to go back to the main, which calls it in the first place. Okay, so I uploaded the demonstration code here. Very quickly, I'm starting again at 0000 hexa with the ljump to main instruction. When it execute, this instruction will jump to this portion here, which starts at 0115 hexa. And this is identical to the previous demonstration code. And with the call, the main will call this subroutine, and this subroutine will in turn call this second subroutine here. Let's see how this thing works out, especially with respect to the stack area. So again, we will look at the data memory. This is the code memory. All right, so let me just step through the program. So the PC is now pointing to 0000 hexa. It's highlighted in red here. So execute this. It jumps to 0115 hexa and loads this binary pattern to P1. We should see the LEDs lighting up. It does. Then it will call this TST code 1, which is this one here. Right now, the PC is pointing to 0118 hexa, which is this one here, this instruction here. Once this gets executed, the program counter should be pointing to 0205, because that's where the next instruction is coming from the subroutine. And this return address should be stored here in the stack. So watch out for PC, watch out for the stack area here for the return address. Okay, step bit. Yes, PC is pointing to 0205, which is this one here, highlighted in red. And the return address is stored in the stack with the low byte coming first and high byte second. So the return address is stored on the stack. Now the program will carry the execution will carry on with the first subroutine. So it will load this binary pattern to P1. We should see the change here. Yes, it does. Then this time, this subroutine here, TST code 1, will call TST code 2. Program PC is pointing to 0208 hexar. But once I execute this instruction, PC should be pointing to 0215 hexar, which is this one here. We should see the change here. But the return address to this subroutine 0208 should appear here in location 0A and 0B, with 0A first and 02 following. Right? Let's see now. So watch out for the PC, which should point to 0215, and the return address 0208 should be in the stack. Let's step it through. Yes, let's look at the stack first. The return address 02 and 0A is stored onto the stack. Remember, it's reversed. Low byte comes first, followed by high byte. And the PC is now pointing to 0215, which is here. Now we execute this, and we should see a change in the binary to the LED, sorry. Yep, they're all lit up, in fact. And then the next instruction here in this second subroutine is an RET instruction. Now this will return to the calling subroutine, which is this one here. How does it know? Because it can refer to the stack for the return address. So watch out for the PC will now be pointing to this address. Sorry, this address. So, yep, it does. 0208, it's highlighted in red. Execute this instruction. We should see a change in the LEDs. Yes, it does. And then now the PC is now pointing to this address 020D, where the return instruction appears. This will then take this back to the main program. And remember, this return address is stored here. So watch it go back here. It does, and it will then load this binary pattern to P1. Again, we should see it change here. Yes, and then it stops. All right, okay. So that's the demonstration for this code here. Well, in the previous examples, we have seen how the stack is used to store the return address of the calling subroutine. There is another purpose of the stack, that is saving and restoring registers. Let's examine this by taking a look at an example. Okay, so here's the demonstration code. Before I start, I'd like to just point out that I've included register bank 0 here on this side of the code, and on this side of the code I have also included register bank 1, and register bank 1 is the designated stack, and its location starts from 08H all the way to 0FH, and 08H is designated R0. Now this is a different R0 from bank 0 because this register 0 here has a location address of 00 hexar, and the whole bank here starting from this point, it stretches all the way up to 07 hexar. And the locations here, the registers are all designated, they're designated R0, R1, R2, and so on. So these two are basically different register bank. although they have the same label, R0, R1, R2, this side, same here, R0, R1, R2, and so on. Now, let's go back to the code. And so as usual, I'm going to start it at 0000H, because on power up, that's where the 8051 expect the instruction. So the first instruction will be ljump main. And main, I have chosen it to start at 0115 hexa. You don't have to do that. You may choose another location, but I choose to start at 0115 hexa. First instruction is to copy 00 hexa into R1. And this R1 is referring to bank 0, because bank 0 is the default register bank when the 8051 power up. So this R1 here is this R1 in bank 0. So, and then copy the contents of R1 to the port 1, P1, and then increment the contents of R1 by 1, and then call the subroutine my code. And my code starts at 0205 hexa. First instruction is to push 01, and this is referring to this address here. So push the contents of 01, or save the contents of 01 onto the first available location in the stack. All right, so so the first available location would be 80H, which is R0 on the stack. 01, if you notice, is actually R1. We can't use the label R1 here because that's not allowed. So we just have to use the memory location of the register location 01. So it's push 01 onto the stack. And then we copy this value on 0F into R1, which is referring to this R1. So the previous data stored here would be eliminated, replaced by 0F, but not to worry, because a copy of that now remains on the stack. When you push the contents of R1 to the stack, physically it doesn't take the value here and move it across. What it does is actually this push instruction make a copy of this and put it into copied it into R0. So coming back to the code here, so copy this value into R1, that replaces the previous contents. Then copy the contents of R1 to P1. Once this is done, it then pops 01. All right. This instruction would do is actually make a copy of this the contents and restore it back to R1 or 01. I repeat again. Pop basically restore the contents that was previously saved on stack and restore it back to R1. It doesn't take the data away. What it does is, again, it makes a copy of what's stored in here and copied it into R1 or 01. Once that restoration is complete, we then go down to RET, that's returned back to the main program. So the program flow or the program control goes back to the main, copy this value to P1. Next instruction here asks the question, is the contents of R1 equals to R3 hexa? If it's not, then you repeat the instructions here, and then it goes down, calls the subroutine again, comes back here, asks the question, is the contents of R1 equals to 03 hexa? If it's yes, then it will drop down to this point here where it says $, and it will remain here, and that would terminate the program. Okay, let's take a look at another example. Again, I repeated the register bank 0 on this side of the code, and on the other side, register bank 1, which is the designated stack. So the program again starts at 0, 0, 0, 0 hexa. First instruction ljump main takes us to this point here, which is the start address, which has a start address of 0115 hexa. First instruction, copy 01h hexa to register 0, and then 23 hexa into register 1. Remember, the default register bank is bank 0. So then copy the contents of R1, which is this one, to P1, then call this subroutine TST code, which starts at 0205. First instruction is the push the value 00 hexa, which is actually R0, 00 hexa, R0. Push that on the stack here. That means make a copy of that, and then copy it onto R0 or the first available stack location. Then we then push 01, which is R1, 01 location R1, onto the next available stack. Now again, it makes a copy of the value of this value stored in R1, copy it into R1 of the stack, and then the next instruction will copy this value A0 hexa into R0, and then copy A1 hexa to R1. So the previous contents will be replaced, but not to worry, because we have a copy of the previous value here on stack. Then output the contents of R1 to P1, and then pop. Notice it pops on restore R01 hexa first. All right, so the contents of that will then be copied, restored back to R1 first, then followed by this 0 hexa, which is R0, the content of R0, put it back into R0 in bank 0. Hope that that's not too confusing. So basically it's the last one in will be the first one out. All right, last in, first out. And then it would then return the control back to the main program, outputs contents R0 to P1, and then jumps and then come to this point where it will stay here. Okay, so let's look at the demonstration now. So let me assemble the code. Switch to the code memory. Yeah, so, and then let's take a quick look at 0115. Yeah, so the hex codes are loaded in. Let's switch to data memory. Let's step through the program. So first instruction, ljump to main. So PC is now pointing to 0115, and the first instruction is to copy 01 hexa to R0, which is also 00. Step it. Okay, so we see 01 here, and we see 01 here. Second instruction loads 23 hexa into R1, and 01. Okay, step it. Yep, 23 is here, 23 is there. Now outputs R1 to P1. Watch this LED. Yeah, okay. Now we'll call this subroutine TST code. TST code starts at 0205. So program counter should point to 0205, and the return address is 011D. So we should see it in 08 and 09. Okay. Yep. So the return address is stored in 0809. Low byte comes first, followed by high byte. Program counter now points at 0205. It's highlighted here. Now, this will then copy the contents of 0H, which is R0 of the bank 0. Copy that into the next available stack location, which is 0A. Watch this. Yep. So 01 is copied here. Then the contents of location 01, which is R1, 2, 3. So step it. Yep, we get 2, 3. So these values now are now copied onto stack. And we can now overwrite R0 and R1 without worrying about the previous value which is stored on the stack. So let's step it through. So A0 goes to R0, A1 goes into R1, location 01, outputs R1 to P1. So we should see that change. Yeah, it changes. Now when we restored this 01H, so watch 01. So this one would that. All right, so we should get 2, 3. Yep. So the last one in is the first one out, then followed by 01. So we have restored the original values back to R1, R0 before we return back to the main program, which is 01. The return address here is 011D. So it goes back, outputs R0 to P1. See this change again. Yeah, it did. And then it drops down to the last instruction, which is 011F, and it stays here. And that's the end of this particular demonstration. Okay, that's it for this video. I've included the code that I've used in this video in the link given in the description below. And thank you for watching. See you in the next video. Bye.